I'm sure you have seen autonomous buses being driven around NTU for testing. The era of autonomous vehicles is not far, and as Singapore gears up to bring this technology to the mainstream, there are still safety issues that need to be addressed. Object detection technology is at the core of AVs. In my FYP, I aim to dive deep in how object detection can become more robust using a method called out of distribution data detection. The previous works in OOD detection have three main drawbacks as listed on the slides. More recent works, specifically a method called detecting out of distribution inputs in deep neural networks using an early layer output, or as we are gonna call it, early layer output method, has been able to address two out of these three concerns by eliminating the need of OOD samples and offering good performance. But it cannot be directly applied to object detection networks. And this is a research gap which I want to fill with my FYP. I want to modify this method such that it can be applied to OD models. Early layer output is a technique which claims that there's a layer in neural networks in which the distribution of the ID and OOD features are well separated. This layer is termed as the optimal OOD discernment layer, or OODL. If we train a CNN model to classify MNIST data and extract features from its penultimate layer for MNIST data as ID and fMNIST data as OOD and plot it in a two-dimensional space, we get the image on the left. If we repeat the same process, but for the OODL layer, we get the image on the right. We can clearly see that the ID features in blue and the OOD features in orange are much more well separated when the features are extracted from the OODL. A classifier can then be trained on the features of this layer to classify ID and OOD data. To eliminate the need of OOD samples, a one-class classifier like OCSVM is chosen to learn the distribution of ID data and classifies any features outside this distribution as OOD. Now, the OODL of any network can be found using this simple algorithm called Algo 1. It requires three datasets. TDS is the training dataset of the original classifier, example MNIST train. IDDS is a dataset of ID samples, example MNIST test, and OODDS is a dataset of OOD samples, example the test set of fMNIST. Now, for each layer in the network, we can train an OCSVM on the TDS features from this layer and test it on a combined dataset of OODS and IDDS and calculate the detection error. We then choose the layer with the least detection error as the OODL. The problem of OOD detection is modeled slightly differently for object detectors. Unlike image classification, where we can label an entire image as ID or OOD, in object detection, there might be multiple ID and OOD objects in the same image. Taking the example of this image, we see that in the same image we have a deer which is possibly an OOD data object, and we have multiple cars which are ID data objects. So the question arises, how to get the TDS, IDDS and OODS to use for Algo 1 to find the OODL. To get the three datasets, what we can do is we can use the labels for bounding boxes provided by the train and the validation set. We can then extract these bounding boxes into separate images using masking as illustrated by the images on the right. If we repeat the same process for each bounding box with ID labels in each image of the train set, we get RTDS. Repeating the same process for each bounding box with ID labels and OOD labels in each image of the validation set, we get IDDS and OODDS respectively. Now, we can simply use the algorithm 1 to find the OODL of the object detector. If we train a state-of-the-art object detection model called YOLO v3 to detect cars and plot its penultimate layer features for objects which are car, ID, and not car, that is OOD, we get the image on the left. Plotting the OODL features gives the image on the right. We can clearly see that the features are relatively much more well separated when extracted from the OODL. The OOD detection for YOLO v3 model across different metrics used in the literature as listed in the table. The results empirically prove that the modifications proposed in my FYP are promising and opens a possibility of modifying other OOD detection methods from the image classification literature. To summarize, we need object detection for AVs. To improve safety, we need to do OOD detection. If an OOD object is identified in the vicinity of an AV, we need to raise appropriate alarms. One limitation of this project is the masking step, in which the context information of an object is lost. In the future, we can look at other methods from image classification or come up with novel techniques which can preserve this complex context. Thank you.